So let's look at a few more examples that involve geometric series. So these last three examples I want to do didn't really fit into the other videos, so I have to just do them separately. But when I show them to you, it should be obvious that they are about geometric series. Okay? All right, so here on this one, I'm going to ask you to use your imagination a little bit. So let's say that there's a swinging pendulum, okay? Like the kind of thing that you might hypnotize somebody with or something like that, or like from a grandfather clock. The pendulum's at rest, it swings about this fixed point, you displace it, you let it go, and it swings back and forth, gradually dampening until it comes to a stop, okay? So imagine that situation. So let's say this pendulum, I displace it from its rest position and I let it go and it starts swinging back and forth. But after release, the first swing, which I've indicated here in red, imagine it traveling through this path over to there before it begins to swing back the other direction. So that first swing is, say, 30 centimeters in distance, meaning along that arc there in red, it travels 30 centimeters. But there's some dampening, meaning that each successive swing is a little bit less than the one that just happened, okay? So if this is just at rest and there's no inputs in it, like there's nothing keeping it moving, then the swing back the other direction isn't going to be as far as the first swing. So let's say here's the assumption with the way that this pendulum works. Each successive swing will be 5/6 of the previous swing. Can you, with this information, estimate the total distance through which the pendulum will move? Yeah, because it moves this way and then that way and then this way and then that way, and very gradually, less and less until it comes to a stop. Okay, so let's think of it like this. The first swing is 30 centimeters, right? Okay. And then the second swing, well, each successive swing will be 5/6 of the previous one, so the next one is going to be 5/6 of 30, right? Okay. So let's think about this. So keep track. Here's the first swing. And then there's the distance for the second. All right. And I'm trying to calculate the total distance that this thing will move. So I got to add the third, but that's going to be 5/6 of the second. So it's going to kind of look like this, right? That's the distance on the second one, and I'm taking 5/6 of that. So you kind of see a pattern already. So 30, 5/6 times 30, 5/6 squared times 30. What do you think the next one's going to be? 5/6 to the third power times 30, right? If every swing is 5/6 of the one that came before it, then that's the pattern that you'll see. And this will go, I guess, on paper forever. Now I know an actual pendulum is going to come to rest at some point. But let's suppose that it just keeps going. Like in every swing is 5/6 times the one that came before it. That gives us a way to estimate that total distance. Now I say estimate because here I have an infinite geometric series. I know in reality this does not swing forever, okay, and it does come to a stop, but you know, at the end it's like not moving very much at all, and at some point the terms here are getting incredibly small as to perhaps be insignificant and so on. So I think, you know, my claim to you is that the sum of this infinite series will be a pretty good estimate to the actual distance that this pendulum travels in practice, okay? All right, so we're needing to calculate that, all right? What's 30 plus 5/6 times 30 plus 5/6 squared times 30 plus 5/6 to the third power times 30? You get the idea. Well, what do we know about this? It's a geometric series. Okay. And what's that common multiplier? Every term in this series times 5 over 6 gets you the next one. So that makes r equal to 5 over 6. And we said in a geometric series, every single geometric series has r, the common ratio. And if that number is between -1 and 1, it will converge. So the sum of this series, meaning what's 30 plus 5 over 6 times 30 plus forever, the sum is going to be, what was that formula? A1 over 1 minus r, meaning the first term of the series, which is 30, over 1 minus r, which is 5 over 6. So that will be the grand total there, which will provide us with a good estimate of what happens to that pendulum in practice, all right? So this is going to be 30, and that's going to be 1 minus 5 over 6. That's 1 over 6, right? And so that will be 180. Okay, now this is a distance. So 180 what? Like it was 30 centimeters this way, then 5/6 back the other direction, then 5/6 of that. The distance measurements were in centimeters. So we'll say the total distance that this pendulum will move back and forth as it does its thing is about 180 centimeters. That assumes an infinity, which doesn't happen in practice, but it's a geometric series and it's a model for what's happening, okay? All right, so let's look at another model that involves geometric series. So this one is also based on some assumptions, but they're not out of line with reality or anything like that. So here's the situation and some assumptions that go along with it. Suppose that 3,000 tons of spinach are grown each year in the United States, which I believe that's roughly correct, all right? 3,000 tons, all right. Suppose also that through improvements in farming and some other factors that are involved, it is projected that we'll get better at growing spinach and not worse, all right? So it's projected that 1.1% more can be grown each year. All right. So we'll grow a little more each year just by improvements. What will be the total amount grown over the next 25 years with the assumptions? All right. Now, so this is an example of a mathematical model. Mathematical models are not crystal balls. Even in our current times when they try to model the spread of a disease and so on, there can be disagreements between different mathematicians with different models because they're not crystal balls. There are a lot of things that we don't know. And when we assume things like 1.1% more can be grown each year, that may only be true for the short term, or it may not be true at all, right? But still, models are useful. They don't predict the future. They're not a crystal ball, but they're useful. All right, they still give us a way to try to look into the future the best we can. All right, so let's think about like this. Here's the way that model sounded. In year one, like right now, we can grow 3,000 tons of spinach, but we're gonna be able to grow 1.1% more in each successive year. So it'll be like the next year will look like this: 3,000 plus 1.1% of 3,000. If you factor out the 3,000, that's 1.011 times 3,000. So right there, that's what it looks to take 3,000 and increase it by 1.1%. Take 3,000, multiply by 1.011. All right. So if I wanted to go to the next year, I would take 1.011 times what I'm at year 2, which you're looking at right here. This is taking year 2's number and increasing it by 1.1%, giving me this number. And I see a pattern like the 3 there and a 2 there, and then I'll get a 4 and a 3. There's definitely a pattern, and this is what it's going to look like in year 25. Okay? Now, so that's just a table to get a feel for the numbers. That's it. That's all it really is. Now, question was, what will be the total amount grown over a 25-year period? So it sounds like then I want to take 3,000 plus the number from the next year, plus the number from the next year, plus on out to year 25. All right? Okay. Now, what I notice about this is a finite geometric series. And for me to calculate this is to calculate a partial sum. This would be the sum of 25 terms of a geometric series. This series, we could continue it if we want to, or we can make it infinite. But in the context of the question, we're finding this, S25, the sum of the first 25 terms. There's 25 terms right there, all right? So here's the formula that I gave you already. For a geometric series, you can calculate a partial sum like this. The sum of the first n terms of a geometric series is the first term times 1 minus r to the n power all over 1 minus r. That's only for geometric series. But if you have a geometric series, this is the sum of the first n number of terms. So in our case, as it is that I've identified that this is what I would like to calculate a grand total of, and I recognize that it is a geometric series, that r, the common ratio, is 1.011. Every term times 1.011 gives you the next term. Then here's my grand total. First term's 3,000. Okay. And then 1 minus r to the power 25, because I'm finding the sum of the first 25 terms there, over 1 minus r. Okay, so there's my grand total. I could add it up by hand, but who would want to do that? We can use the formula as a shortcut. So if you do that, let's see, where's my, okay, calculator. Here's what you'll get. 1 minus 1.011 power 25 times 3,000, and then I divide, and I get about 85,787. Let's round to the nearest ton. So about 85,788 tons. That's the total amount of spinach that can be grown over a 25-year period with these assumptions. How about this for comparison? Let's say that we're not able to improve our farming, okay? We can't grow more each year. So let's see, what would it be like then? Well, then it'd be like, say we grow 3,000 this year and we think we can do about the same every year on into the future. So just for comparison, let's take 3,000 and times 25, we grow 75,000 tons. So that's the, we get 15,000 more tons over that 25-year period with the assumed improvement, assumed gradual improvement each year. Okay. All right, so factors involved in this one. Do you recognize how we can calculate year by year? Do you recognize the grand total that we're looking for? Can you tell it's a geometric series? And did you happen to remember that there was a formula for calculating a partial sum of a geometric series? That's what we have there. Okay. Now, let's look at one more. So this one, this is just kind of a weird looking series that I didn't want to include anywhere else. But I'll tell you, does this series converge? If so, what's its sum? So this is an infinite series. Notice the ellipses. It goes forever. Is this geometric? What's a geometric series? A geometric series is such that any term times some number r will get you the next term. So for example, in this series right here, if you take the first term, 3,000, and multiply it by 1.011, you will get the next term. If you take that term times 1.011, you'll get the term after that. That's what r, the common ratio, is. This is not like that. I mean, I can see like a half times a half is a fourth, and a fourth times a half is an eighth, but 5 times a half is not 4, and 4, whatever you multiply 5 by to get 4 is not the same thing as what you multiply 4 by to get 3. So This is not a geometric series, okay? But I noticed that part of it is. I guess I could look at like this part of it. That's one way to do it, okay? Just that part is a geometric series. So look at the whole thing and then think about it like this. And there it is. That's how we want to look at it. These don't fit the overall pattern of being geometric, but from here on, there's a pretty well-established pattern. Okay? All right, so yes, that number is just 15, but a half, a fourth, an eighth, a 16th, a 32nd, that's a geometric series. It's a geometric series with a first term of a half and r, a common ratio also of a half. So you could take 15 plus whatever that adds up to. That's the way you could do this. Now, this particular series I've used in a lot of examples so far. It converges to 1. So it converges to 16. Okay. All right. So does it converge? Yes, it converges to 16. Okay. Yeah, so if you took 5 plus 4 plus 3 plus 2 plus 1 plus a half plus a fourth, plus, up to there, your grand total is 16. If you keep going very gradually, this much of it, your answer, every time you add that next term, will get a little closer to 1. So that's why I can say the whole thing adds up to 16. Converges to 16.